Yeah, welcome students to another lecture of friction. Last time already I told you about the introduction of friction, the definition, and the kinds of friction. Hope you saw the previous video. Today we are going to start from page number 271, and we are going to go a little ahead of the same concept. Motion along a rough inclined plane. So what happens if a body is moving along the inclined plane in its own weight? So please write down motion along a rough inclined plane. That's a main topic, and there's a part of it. It says body is moving along the inclined plane due to its own weight, right? So draw the diagram here. So consider there is an inclined plane of angle theta here, and you have the body which has a mass m. So the weight is mg. We already know this one. Weight is always like this, and also we know the normal reaction will be in this direction. So this normal reaction is here like this, and this is the value of theta here, which is going to be mg cos theta, and we know this is going to be mg sin theta. These all things we know already. Now this body is moving in its own weight. It is just coming down. Because of this coming down, what is this direction here? You will have a frictional force which is there in this direction, which is called Fk, because it's a kinetic friction. Now this diagram you need to make. So then write down these lines. Let theta be the angle of friction, or angle of the inclined plane. Let theta be the angle of inclined plane, and mg the weight of the body acting vertically downwards. The normal reaction. What is capital R is equal to? Capital R is equal to, straight away it is opposite to mg cos theta. So we find these two are opposite to each other, right? Now we know write the next line. As the body moves down in its own weight, the frictional force acts opposite to the motion. Fk is equal to mu k into r. So we know what is mu k. Mu k means it is the coefficient of friction, kinetic friction, and r, which is equal to mu k into mg cos theta. So this is Fk. Right, this one you can put it as equation number 1. This is equation number 1. So now the body is moving down in this direction here. So the frictional force is in the opposite direction. Now taking the force along the horizontal of the inclined plane. The forces along the horizontal of inclined plane. So mg sin theta, mg sin theta is acting in this direction, and opposite, what is the value? Mg sin theta minus Fk is equal to what? Is equal to mass into acceleration, which is the actual movement of this one, the way in which it moves. Now Fk we already know from equation 1 here. So mg sin theta minus mu k mg cos theta is equal to m into a. So this one we are picking it up from here. So exactly I would just drop down the same thing. Now it looks a long equation, big equation it looks like. So mass gets cancelled out in both the direction. If you take mass common outside, this mass and this mass can get cancelled out. So you get here the next expression is g sin theta minus mu k cos theta is equal to acceleration. This is the acceleration formula. When acceleration is 0, when this body moves in a uniform velocity, when acceleration is 0, there are two areas. If it is uniform velocity or at rest. So anything could be possible. When acceleration is 0, so what will happen? G sine theta minus mu k cos theta is equal to 0. So what you can write the next line? It is G sine theta is equal to mu k cos theta. So what is mu k is equal to? So you get here the next line is mu k is equal to G sine theta upon cos theta will be the value here. So mu k is equal to G tan theta. So you will get that as an answer here. Right. So one thing I think I missed out here is G value I missed out here. Sorry about it. G value I missed out here. Here also G value I missed out here. Right. So G also goes here. G also goes here and G gets cancelled out. So there is no G here. So you get here mu k is equal to just tan theta is the value here. Okay. So this is when the body is moving down in its own weight. Right. Please pass it, listen again and try to very well understand the basic concepts here, and it is very, very important derivation. Okay. Now we'll go to the next part of it. So we move forward to the second part of it, B part of it, when you apply a force. Earlier it was moving down in its own weight. Now you apply a force and the force is applied downwards and the body is still in an inclined plane. So how it will relate is, again draw quickly the same diagram. You might have to draw it several times. Make sure this arrow marks are all very, very clear and straight. So this is mg and we know this is going to be r, and we know this comes like this. This is theta here, this is also theta here, and mg cos theta, and this is mg sin theta. Now this one is here like this. Along with this one, our force is applied here. So this force we can call it as P. P is a force which is applied here. Now there is a frictional force Fk will be acting exactly opposite to this one, and here you have normal reaction. So same things again, it is same things are there. What is theta? Angle of the inclined plane. What is mg? The weight of the body acting downwards. What is r? Normal reaction. So normal reaction when it is there, so you can write here as r is equal to mg cos theta. We already know these two are opposite to each other. Keeping this in mind, Fk, the frictional force, frictional. So these are the basic things which we need to write. It is equal to mu k into s into r. The formula of friction is the coefficient of friction into normal reaction. So it is mu k into mg cos theta. So this is the basic thing. Always you need to first of all fill up this whole thing. So this is equation number 1. Now we will go to the main part of it. What happens here? So you have two things are here in this direction here. Now these two are pulling in this direction. One is going the other direction. So along the horizontal, what happens? P. What is P? P is the force which you apply. Now I can write down along the horizontal. Let P be the force. Let P be the force applied. Now P plus mg sin theta. There are two forces are acting together is equal to, what is the thing which is here in opposite direction? That is the opposite here. You cannot say equal to. I could say that is kind of it is going in an opposite direction. So it's equal to Fk. But you cannot really write this equation at all. It's not this is two things is not balancing this one. You can never write this way because frictional force is always subtracted by anything. But to an understanding, I have just written this one, but later on we need to cancel this expression, never write this expression in the examination. So what we write is external force is equal to, this one goes there, Fk minus mg sine theta. So this equation we just cancel out. Don't write this equation. It is for just for an understanding, because these two are there, but these two can never be equal to the frictional force, but frictional force minus this one, it is equal to mg, we have written. Now this particular part of it, equation number 1, has to be put here in this expression, mg, it is going to be mu k into mg cos theta minus mg sin theta is equal to p. So what is p? That's going to be equal to the external force here. So it is equal to, here what you can take it out is mg, you can take it outside, so it is mu k cos theta minus sin theta. So that is going to be equal to p. If you want to write the work done, what is work done? Work done is equal to, if you move for the small distance here, it is going to be equal to p into a small distance. So work done going to be equal to mg into x mu k cos theta minus sin theta. So this is the final expression for us, right? So this one, you have almost the same thing only thing is, instead of mass into acceleration, you have got an external force which is here, and the things are quite reversed. But remember, when the force is applied downwards in an inclined plane, so this body is just going down, and you can easily find out the work done. The force, external force is applied here, and you can find out the work done here, right? And the external force is something extra. Don't write as m into a. Alright, of course you can write it as m into a also, because you can find out the acceleration. If you want to write m into a, it's well and good. So it gets cancelled out, and you can finally get out what is the thing. So because you are externally driving it with a greater force, that's also possible. Now look at this one, C part of it. What is C part of it? When the force is applied upwards for a body in an inclined plane. Now what you do is pause the video and draw a diagram with another topic. Write the topic, upwards you write, and then instead of P down here, you're going to put it up here. And draw this diagram here, and you need to try to derive yourself. Go ahead quickly. Now pass it. Make the diagram and do it. So here I have drawn a diagram for you with the upwards is the topic here. Now where is the frictional force acting here? So force, external force acting here, frictional force is going to be here as Fk in opposite direction to the thing. The entire body is going up. So we know already R is equal to mg cos theta, and then frictional force Fk is going to be equal to mu k into R. It is mu k into mg cos theta. This is the equation number 1. So this is Fk. Now you need to know what happens in this condition here. So what is P is equal to? So P is dragged. Let P be the external force. So P is dragged by these two forces, mg. So you get mg sin theta plus Fk will come here. So mg sin theta plus Fk, mg sin theta plus mu k mg cos theta, that's P. So P is equal to mg, you take it common outside, sin theta plus mu k cos theta. Work done. What is work done? W is going to be equal to W P into the x is the distance, so it is mgx sin theta plus mu k cos theta. That's work done. You can even take this as acceleration also, m into a. If you put an acceleration you will get, and mass you can cancel out. So that's the way it happens. When the body is moving up above in the inclined plane, you will get plus here. This will be plus. Now last time when we saw, when it is not going up above, then you will get here as a minus sign. This will be minus. So mg cos theta minus this one will become, now here you are getting mg sin theta plus you are getting as a symbol here, right? Now we are going to the next case. Look at children, this book does not have the next two things that I did, work done, moving above and moving down. So but it usually comes in the examination, so I have done that one. So only A part is here. Now we are going to the another part called, what if the force is given in an angle here, right? So the one gap in this book is they have not given the middle part of it, but I have dealt with you. Now motion in down an inclined plane, the body is going down an inclined plane, but look at this particular part, what the force they have given here, in which direction the force have given here. So they have given a force F. The diagram shows the force is given not along the inclined plane but in the angle here like this. So now we are going to do this derivation, which is little different than what we have done. So the first two things will help you to do that. So the motion is when the body is moving down and upwards the inclined plane, and when the body is moving down an inclined plane. So when this one is quite simple here. Now P is acting here. What if the P is acting here like this? So that is a little more complex. So once you have done this one, it is very easy to understand that one. So we have already done this. You have 2 and 3 derivations in this inclined plane. The fourth one we are going to see. The fourth one is when the force is applied downwards. So the D part is when force is applied in an angle alpha to inclined plane. So the force applied with an angle inclined plane. So draw this diagram here. So this is the body which is here, and this is already theta. This is already theta. Now the body will definitely move in this direction here, but a force is being applied here. It could be any angle here. Don't think it is just should be like this. It could be any angle also. Force can be in this direction also. Any angle could be there. So as a force is applied, we call it as alpha. We don't call it as same theta. We call it as alpha because it could be any angle here, right? So now we need to, this is the external force, capital F here, or maybe you can call it as P also. That's also a nice idea here. Now we will try to draw the full diagram, how this diagram will work. So be very careful about the basic system. Basics are remaining same, but there are some major differences you will find. So we draw this diagram here like this. There is an inclined plane and the body is here. This we already know, theta here, mg, and normal reaction. Please make sure the lines are straight and proper. And this one is mg cos theta always. This is theta here. And this one is mg sin theta. This is the basic thing. Now a force is being applied here like this. This is capital F. And this force is making another angle here. The angle here is alpha. Now this force can be resolved into another 2 components, here and here. Now look at this one, and the top of it, one more problem is happening here, that you need to deal with the capital F already in an angle here. When the angle is 0, when the force is not in this direction, it is along the plane. That's simple. Already we have done it earlier. But now it makes a little more complex. So write down the force also. What is the force here in this direction? This will be F sin alpha. And this will be, here is F cos alpha. Please make sure there are 2 angles, theta and alpha. Don't confuse. Now when the body is coming down, what you will get here in this direction? The value of frictional force K. F K will be there. Right? Now all things are set now. You can write down few steps now. So what is mg? The weight acting downwards. And then what is r? Normal reaction. Now normal reaction. Now the usual thing that we write, you cannot write now. It is little different. Now we need to be a little careful about what you're writing. So what is that in the horizontal, in the vertical here? So r plus f sine alpha is equal to mg cos theta. So this is along vertical. Okay. Now what do we write here? We write also normal reaction, and capital F is the force applied. So we write this equation you can name it as equation number 1. Now the next equation is what happens in the horizontal. So horizontally you have two forces here, and Fk is in the opposite direction here. So how do you write here? As now going ahead, mg sine theta plus f cos alpha is equal to Fk. So this is the equation number 2. Now we need to rely on both the equation and then do it. So what is equal to? This is going to be equal to mu k into r. This one, it is coming here. So first equation can be written as, look at the first equation. What can be written as? This one can go here and then r will be here. So what is r is equal to? First equation is now, it is coming as, what is mg cos theta minus f sine alpha. So it is equal to mg cos theta minus f sine alpha. So that's going to be mg sine theta plus f cos alpha. So this is the way in which it will be look at. Look at this one. The equation is quite big now. F cos alpha, f sine alpha, mg sine theta and mg cos theta. Now where is mu k? Mu k is here. Don't forget to put mu k, and this is entire is in the bracket here. Right? This is the coefficient of friction. Now f cos alpha and f sine alpha, bring it to the one side now. So f cos alpha minus, so when you multiply this one inside, so it is going to be f into mu k sine alpha. It is a minus sign. When it goes to the next side, it will become plus. That is equal to, now this one is together, mu k mg cos theta. It is this one, and this is going to the next side, minus mg sine theta. Looks quite big. Doesn't matter. It will be solved soon. Now take it common outside. If you take it common outside, it is cos alpha plus mu k sine alpha is equal to mu k mg cos theta minus mg sine theta. So this is f is equal to mu k mg cos theta minus mg sine theta. The top remains same. This one goes down. So cos alpha plus mu k sine alpha. So this is a big expression that you get at the end of time. Right? There is further simplification is there. I am not doing that. There are further simplification is there, but the book has done it. So I think this is enough to express how an angled one will make. There are two angles, alpha and theta is there. So with this, it is much better to stop here. If you look at the book is going a little further down, and then finally trying to make a final expression of mg times of sine theta s and minus theta. This I will not try to venture out. It's okay. It is already quite complex. That's enough. So with this, the inclined plane, all the 4 cases gets over. Right? Please make sure you differentiate nicely and read it properly. Okay. Now we go to the next topic now. So this topic is number 7, pulling and pushing of a roller. Imagine a big roller which is there in the ground where it is used to level the ground. So either pulling or pushing. So the question is, which is easier? Is it pulling is easier or pushing a roller is easier? And we are going to take friction also into account. So first of all, we'll do the case of pulling a roller. So the first case is pulling a roller. So make a diagram like this. So there is a roller. We are going to take the cross-section view of this one, and this roller is at the ground. So only a small tip is now it is here. So you have a roller's handlebar is here, and you have it. So this is being, the force is being applied here. So when you apply a force here, you apply a force along with an angle here. Now we know there is already a weight of mg acts downwards. We know this one, and the reaction already acts upwards. So this F, the external force, can be resolved into two components. So what is this value? This direction, F cos theta, and what is that above direction here? And this is going to be F sin theta. Alright. Now this whole body, it goes in this direction here. The direction is in this direction. This is an acceleration here. Which direction the frictional force will apply? The frictional force applies here. It is Fk. This is a frictional force just been applied here. Now we need to resolve this one accordingly. Alright. Now what happens when the acceleration is in this direction? So you can write down, consider a roller which is being pulled by a force F with theta as an angle. So resolving into two components, F cos theta along horizontal and F sin theta along vertical. So along the vertical, what happens? So R plus F sin theta is equal to the weight, that is mg. What is mg is equal to W here, right? So what is R is equal to? W minus F sin theta. This is capital F. Now what is the frictional force? Fk is equal to mu times of R. We know it is mu times of R. What is R? It is already here. So mu k times of W minus F sin theta. That is the frictional force. Right? Now tell me, which is easier now? How is it easy? Usually whenever we drive this one, it is mu k into mg will be there, because R will also be equal to mg. Now this frictional force is being subtracted by something else. Whenever you pull the thing, you have a subtraction factor to the friction. So the friction is not much. Friction is subtracted by this much of quantity. Because of this reason, the pulling of a roller is much simpler. When you pull, it is much simpler. So you can write down, since F sin theta is subtracted from the weight, so the frictional force is less. Friction is less. Hence, it is easier to pull a roller. We'll see the next case while pushing a roller. B part of it. While pushing a roller. So similarly, make a diagram of a roller. So there is a roller here. Now you are pushing the roller here, and this is a handle here. Now this handle, you wanted to give a push here. The push here will give a force in this direction here. When you give a force in this direction to the angle theta here, you already know the weight is acting downwards, that is equal to mg, and you have the normal reaction, capital R, and the wheel has to move. So when you're pushing, it goes in this direction. It goes in this direction here, right? Now this is F cos theta, and here it is F sin theta. So this is the two components which is here. So once you are pushing in this direction here, so what happens to the rest of them? Right. There is a mistake here. Look at the mistake. What is the mistake is? Don't make this diagram. This diagram is wrong. This force is actually acting in this direction, downwards. So since the force is acting downwards, you will not be this F cos theta will not be in this direction. F sin theta will not be in this direction. It's actually going to be the other opposite direction here. So remember, you can very well easily go wrong when you are trying to do a derivation. So I'm redrawing the same thing, okay, with the same kind of a concept. Please redraw it. The pushing of a roller. Again, put a roller here. So there is a handle here. So you try to give a push here with an angle theta here. That's fine. W is definitely acting here. R is in this direction. This will go here. Right? When this is going here, this is F. So when this is coming here like this is going to be theta here. Theta is here. Now when theta is here, this is going to be F cos theta. And what is going to be this one? F sin theta. So you find in normal reaction, F sin theta and W are together. Alright. So write down now. Consider the force is applied downwards in the push direction. Pushing this one, and the wheel moves and the roller moves, resolving F into two components, F cos theta along horizontal and F sin theta along the vertical. Along the vertical, what is the force? R is equal to F sin theta plus W. That's what the thing is. So what is the frictional force? Fk is going to be equal to mu k into R. So mu k into R is this whole value, F sin theta plus W. That is frictional force. Now the frictional force is less or more. That is added here to the weight. F sin theta is added to the weight. Look at the previous case. The previous case was the weight was subtracted by F sin theta, but here the W was that if W and an F sin theta is added here. Because of this reason, the frictional force will be very, very high. Since it is very high, it is very difficult to push a roller because the frictional force will not be trying to cooperate with this one. So you can write down, hence, it is difficult to push a roller since the frictional force is very high, as F sin theta is added to the weight W. When you look at this book here, they have done little different. I have not done the same way. They have done theta in this direction. Whereas what I have done is, I have done theta in this direction along the horizontal. So always we have been taking horizontal. So I have taken that way. So it is not F cos theta, it is here up. For us it is F sin theta is there. No problem because it is taken here like this. When you resolve like this, the formula little changes, no problem. Here it is subtracted by F cos theta because we have taken theta here. I have done it as F sin theta. So here also it is addition of F cos theta here because they have taken as a theta in the top direction. Either you can do this way or you can do that way. Both of them are correct. Alright. So that's the way it is. Now I would say the last few part is there. Friction is a non-conservative force. So what is a non-conservative force is? So it depends on the force depends upon the initial and the final position as well as the path adapted is called non-conservative force. So what is the conservative force is? The force, it depends only on the initial position and final position. It does not depend upon the route which you take. If you push here and then push in one place and then you take it to the next place, so if the entire route, wherever it takes, force is not, you are not going to take into account, then that is called conservative force. Non-conservative force is wherever the route it takes, everything is counted, that is called non-conservative force. So friction force is a non-conservative force, you should understand that. So it depends upon the initial and final position as well as the path adapted, that is called this one. So it is important to know friction force is a non-conservative force. So they have done a small derivation here. Force is equal to work done into the distance, and here it is cos theta is 180 degrees. It is 180 degrees. What happens here? The force is acting like this. So this is the direction of motion, and the frictional force is acting in the opposite direction here, F. So what is the angle between these two forces? It is 180 degrees. So the work done and the angle is 180 degrees. So you get here 180 degrees. So W1 is equal to mu K into mg into d will be there. The net work done will be like this, right? So frictional force is non-conservative, and even if you again go back and come back to the trip, make a round trip from A to B you go, and from B to A you again come back. So that's what they are doing. From A to B they've gone, and B to A they are coming back. So F into D. So they are having it as a negative sign here. Of course this is a negative sign because it is 180 degrees is there. So the total work done is going to be definitely, it's going to be equal to how much? The total work done, it is not zero. In the friction force, total work done is not zero. In the conservative force, what we say is the net work done, finally go and come back, then work done is zero. But the net work done during the round complete trip is W1 plus W2. So mu K into mg into distance minus of mu K into mg into distance. So you get minus mu K to mu K mg into d. Please note down this. It is very, very important. It is friction force is a non-conservative force. It doesn't cancel out. The net force is not zero. The last two parts, did you already know this one? Frictional force is a necessary evil. You would have studied in 9th standard. Please read this one. And the methods of reducing friction. There is a polishing, there is lubricant, and then there is proper selected materials to reduce friction. So you can just learn, just read this one. So with that, this particular section gets over, and also you have the streamlining, and using ball bearing also you can reduce the friction. So with this, the frictional part gets over, and then we'll go to the numericals now. Okay, thank you children. So we have done extensively this part, and let us go to the numericals in the next class. Thank you.